Thank you for joining the Once Changing the World, India's first Future Tech Meets Sustainability podcast. And today I'm delighted and honored to have with me Dr. Subrata Ghosh, who is a principal scientist and associate professor at the Chemical Science and Technology Division at CSIR Northeast Institute of Science and Technology, and is a faculty member of chemistry at the Academy of Scientific and Innovative Research. His research interests include organic synthesis, drug discovery, nanorobotics for treatment, and neurology. His contributions include the development of anti-cancer nanobot drugs, double-ratchet molecular motors, resonance frequency technology for curing Alzheimer's disease, and multi-channel molecular engineering for self-assembly of organic nanomaterial. So today the subject of discussion is going to be breakthroughs in chemistry and nanorobotics for healthcare. So, Doctor, really appreciate you taking time and being part of the podcast. It'll be nice if you could start with a brief introduction, your background, and your research works.
Thank you, Eddie. And thank you giving me the opportunity and inviting me in your podcast. I'm really great. It's my honor to be present here and discussing with you regarding my research activities. As I already mentioned, that nanobot drug discovery, that is the prime objective of my research area. And beside that, also, as I'm an organic synthetic chemist by practice, so basically natural product molecules are some phytochemicals or other metabolites, secondary metabolites, which are obtained from the plant sources. But for the last couple of centuries back, it was a great area of research to develop the laboratory synthesis method of those natural products by designing a new scheme. And it will be helpful for the drug discovery world also, because a lot of natural product molecules are active and they show very good activity in the biological systems for against but the limitation is that you cannot collect them in large amount from the natural sources sometimes, because you need to cultivate your plant which you are using to extract a molecule. So scientists decided, organic synthesis chemists decided to synthesize those same type of molecules in the laboratory. So that was my training, and I was working on that for the from 2003, and then I completed my PhD in that topic. So after that, I started my journey as a postdoc, and then immediately I submitted my thesis. I got the opportunity to go to National Institute for the Material Science, Japan, where Dr. Anirban Bandyopadhyay hired me as a postdoc, and I joined him around 2009 October. So there, actually, this nano brain concept I come to know first time, because before that I was not so much aware about it. But later, when I joined his lab, his discussion and all those kind of research activity I observed very closely, and I saw he's passionate to design a device which will be self-sustained, which will be artificially intelligent enough to survive in a difficult situation in the hostile environment. It can take its decision also, and then certain job it can uh, deliver. In the discussion, I come to know that in 2008, when he first observed this kind of interaction in the molecular scale, he explained it to me. Dr. Bandyopadhyay said that, see, we have observed, and you can go through my paper, and there we have already discussed how a completely different environment in the nanoscale environment under the microscope, we can observe molecule and how one molecule interacting to the other molecule. And in this way, in a completely circularly assembled molecular structure on the surface, one molecule, if we induce by some information means you can induce by some electromagnetic wave, you can induce by some electron volt or something, then that molecule start interacting all the surrounding molecules at a simultaneous time. So that was very interesting to me. And then I went through the paper and I come to know that, yeah, so this is a very beautiful observation. Obviously, it's a high quality science. And then he explained that, okay, Subrata, now this is on the surface bound only. So we need to take a structure, we have to develop a new architecture which can be so similar kind of molecular level interaction and higher level of dynamics and intelligence, but in space, maybe in solution, maybe in the air, maybe in some surface, freely moving. So there we planned this nanobot concept, because nanobot drug is not a particular type of materialistic drug. It's a concept. So there, initially, when we started, we observed that, okay, so we can choose certain kind of molecules which we can assemble together, and that may evolve certain kind of electromagnetic level of intelligence which can be useful for our purpose. So we started with Pamam dendrimer. Initially, I work a lot of literature search on that initial days. And then I found that dendrimer is a very potential molecule for my purpose, because it has a huge network. It is a starburst structure and spherically symmetrical also. And there are certain cavities inside the molecule, as well as the branching is like neural network. And there at the terminal, you have open functional surfaces where you can immediately plan to attach something separate entity according to your choice. So there the journey started.
Yes, so Doctor, really appreciate sharing your journey, explaining your work, in synthetic novel molecules, organic synthetic chemist, and your partnership with Dr. Anirban Bandyopadhyay and NanoBrain. And yes, I think the world, I mean, normally, we look at the macro world, when we go into the micro world, it's so deep, it's opening up these new spaces that, the more we peer, the more we kind of get to know, and understand that the micro world, the nano world is doing things which is so amazing. And here you are, trying to kind of tinker around with the nano world and building these nano bots and things like that. Before we get into nanobots and drug discovery and things like that, you pointed out something very interesting, that when you're working with in Japan with NIMS, they are they've really created a environment which is very conducive for researchers and entrepreneurs. What are your thoughts on India's ecosystem? Because there's a lot of these breakthrough entrepreneurs, researchers, and professors such as yourself. Are they getting the right due? Are we creating the right conducive ecosystem for the bright minds such as yourself to flourish and thrive here in India? What are your views on that?
Indian science is going in a faster speed now. I can see that, because a lot of young minds has joined the group, and not it is not limited to only the organization related to government only. Many private party has come up in this domain, and they are playing the key role for developing this Indian science. And as well as you also already mentioned about the startups. To inculcate more scientific mind, I think facility is required, because until this mobile revolution came, I was very not sure that whether what level of interaction we are doing this day, you and me, and any scale of from a village to the city to the international global level. This connecting world has been created by this mobile revolution, and there the private party has given us the opportunity to do this. But in the lab scale level, if we want to work more into the system arrangement, then what we saw in outside country, like, see, I'm in Japan, I already told you that there is a facility in the system where you can easily get access. So that kind of system we can also develop in our country at our research organization, because that will help. What I am telling you, it is not make the scientific activity limited to the researcher or scientist only. It will open the door to all. And anybody has certain ideas, has their open mind to do something creative, they are not stopped to go ahead anymore, because they will immediately connect to that system and they will come and explore their ideas. And there is a huge possibility. If you make the numbers of scientific mind in a huge amount, then definitely your chances of getting output out of that scientific advancement would be much higher. In Japan, I'm telling you, the whole nanofoundry system was given charge to a engineer who is the head of the system, and he has no interest about the research. Even you told him, I mean, if you say to that person that, okay, sir, I use your system, if I give it, give something back to you, can I refer your name in my citation of the paper or somewhere? Acknowledge you. Even acknowledgement, they don't accept, because they are not interested in that. And they never say that. They even try to stop you. No, you don't put acknowledgement of my name. Even if you want to do that, you put NIMS Nanofoundry. That's our price. So this kind of human staff also required
Culture.
to maintain that system. That culture is to be in the system, so that this culture will immediately help the whole system to grow in a different way,
True,
which
true.
is actually not, I mean, very common to our Indian scientific domain.
Right. Yeah, I hope, doctor, that that kind of changes, because we celebrate these artists and musicians and actors, and there's nothing wrong in that. But I think we should also start celebrating the entrepreneurs, the researchers such as yourself, because I guess everything that we use or experience, or the tools today are a product of these innovations and breakthroughs done by researchers such as yourself. So, and I think we're sitting in such a fantastic point of time where all of these technologies are going to play such a huge role. So I think the government, the academic institutions, the entrepreneurs who are the front runners of the ecosystem should be supported, should be given a, a great ground to play, so that I mean, they can create products, services, and solutions which can be leveraged globally. So I hope that kind of changes. Now, obviously, you kind of gave a lowdown on your work with synthetic novel molecules and work in nanorobotics. But I think it'll be great if you can ground our audience, and giving them like a very basic understanding or the concept of what nanorobotic is in a layman's term, and some of your work in nanorobotics.
First, I'll like to mention for the layman purpose that what is actually nanorobotics and what we nanorobot can do. So if you have a robot in macro scale, there are a lot of electric circuits, and those circuits are designed with certain purposes, and those are activated and deactivated with time scale. And that's how a total movement of that robot works. And it has no brain still now, but software is designed in a way that with time gap, it will act in a way so that it shows some human being like behavior. But it is also in the developmental stage. We have seen that still the robot is already implemented in hotels to serve food and other things. But if you challenge them with little difficulty, they can solve it. So those macro robot is designed with the electrical circuit, but in nanoscale, you have that limitation. You can't plan to make circuits so complex manner that it will activate and deactivate or maintain whole system, because it's a molecule only. And molecule one atom to other atom distance is only a few Armstrong. So we have not come to a point still now to design a circuit of Armstrong size. So there you have a limitation. So what you can do, you can conceptually make it. How? So I'm explaining it. So as you need a decision unit in a robot, and similarly you need a sensor unit there and one functional unit there. So these three component, if you bring together in a single system and with certain external input like maybe light beam, maybe electromagnetic wave, other type of thing, magnetic field, or if it is better to if it get activated and deactivated automatically in the thermal environment only, because thermal and radio, this type of energy is abundantly available in the nature, so we need not to supply it separately. So if I can design that kind of architecture where it will get energy from the natural sources only, and it will operate its all these three domain with that energy circulation or that energy triangular energy pathway we say, because one sensor, one controller, and then one functional unit. If we can connect them and it get operational, then at the primitive level, you can say it will show some kind of intelligence, which is actually the concept of the nanorobotics. So for any layman, if he wants to design a robot in nanoscale, then these three things, three units need to be maintained first. Then you can add some accessories also with this primitive system. So there it is the first thing. Next, that whether your artificial system is so intelligent that it can solve a problem, that you need to test in the real time. So there you apply your material to some challenging problem, like we did, suppose in case of nanobot, we treated it with cancer. So cancer cell is an environment which is distinctly separate from normal cell line. But if your material is really intelligent to sense that kind of micro change in the environment, that cancer is different, normal is different, then it can work accordingly and positive, negative result will be get. So this way you can uh, understand what nanorobotics is. But it is
Right.
not limited to only drug discovery. It can be used to many ways, like material development. Suppose you want to uh, make a material in a design, which is you have planned to design, but you cannot make it with some this 3D printer also. And there you have to make your basic unit intelligent enough and program it in a way so that the energy dynamics or vibrational dynamics of that particular unit will particularly, immediately evolve in a way, and you will get a assembly of that design. So this kind of thing you can carry out with this kind of nanorobotics.
Would you be able to give some kind of a reference on what a nanoscale is? Because when you're talking about the macro world, we know that when you're building a robot, it's these large robots, which is humanoid robots, which you can see, experience. But when you're talking about nanoscale, will be great if you can give like a uh, like a reference to an audience. What do you exactly mean by a nanoscale, and how down are we going over there? Yeah.
Yeah, correct. Yeah, so definitely. We give the common example of hair. So hair is a micrometer size. So now if you splice the hair in a way it's get down and down in size, cut the cross section of plants in our earlier school days, and we observe under the microscope. So many people has maybe expertise as well as the experience of that kind of practical laboratory experiences. So they can understand how small the cell is. That cell is micrometer size. So this here is millimeter size, that cell is micrometer size. Now under that microscope, when you see the cell clearly, you observe certain domain where a nucleus is there. So nucleus is also in the micrometer domain. Now, if you go more downwards, and then you will design a structure where a complex protein is there. So protein is a structure which is comes in this nanometer size or some Armstrong size. So those protein are inside the cell, but you cannot see that protein inside the cell. You can see ribosome, you can see some cell organelles, vacuole, other things, but you cannot see protein also. But those protein altogether make certain kind of structure, which is maybe ribosome, maybe some other stuff. DNA, you can see the DNA also. But in nucleus, there are chromosome. You cannot see chromosome also. So inside the cell, chromosome is not visible. Inside the DNA is there. DNA is so small that you cannot see them under normal microscope. So you need to go to higher version of microscope where you can see DNA also. So at that level, when you go down, then you come to get some atomic strip, long strip like tape. And there are several billions of atoms existing in the chromosome inside the DNA. And DNA, there are nucleotides. So that nucleotide has certain base pair and some string like chain. And that base pair is a molecule now. So now you enter into a molecular domain. And that molecule is, the base is actually in the Armstrong size. And there are certain atoms arranged into that structure, which actually giving a certain kind of dimension of the molecule or structure of the molecule. So that is Armstrong level. And now how you see that atom, because you can see up to the DNA at a very high level of microscope. But beyond that, if you want to go, then you have to take help the scanning tunneling microscope. So scanning tunneling microscope is not a visible microscope. It's not a just optical microscope. It's a electron. By putting electron into a molecule, you evolve the electronic environment of that atomic structure, which is we call molecule, and that electronic behavior is captured by your detector. And there you reproduce the structure in a shape, and that you give the structure of the particular molecule. So you can see the silicon, you can see how carbon, graphene looks like, how this other molecule, any molecule you can observe under that microscope. So now you have already understand that how small domain we are talking about, the nano. So now you can easily get how nano size is, and beyond that there are pico, femto, and other things.
How beautiful, because I mean, it's kudos to scientists and researchers such as yourself who are like going down to the bottom of things, going down to these nanoscale, and then, to kind of tinker around with the molecules and possibly the source code of life, and building out these nanorobots. You gave some insight on your work with anti-cancer nanobot drugs. Could you elaborate on that? And it'll be nice if you could talk also about the applications of these nano drugs, nanorobots, and drug delivery, because when COVID hit, RNA was used for drug delivery. So I think it'll be great if you could kind of explain how these nanobots, nanorobotics are being used for drug delivery also, besides your anti-cancer nanobot drugs.
Okay, so here I'd like to mention first that this nanobot and that nanorobotics we are talking about is little different in concept, because generally the nanobot people used to develop for drug delivery. You can use certain kind of synthesized structure as well as some available biological structure also, because if you go by the literature, and particularly I would like to mention that the book Engine of Creation by Eric Drexler, there you can see that he has mentioned about it, that the biologist has no access to that domain where they need to go, but only the access is their cell material, because from cell they can extract some material and then it can be used. So ribosome is these days used as a drug delivery system also, uh, and liposome you have developed, then micelle you have developed. So all are size wise in the nanostructure, and but these are not actually intelligent system. Those are kind of a cargo system where you can put something into it or on the top of the it, and you put some sensor and other things to just send it to a particular target. Here, this nanorobots, what we are talking about, is not a drug delivery system anymore. It is itself a evolving drug. Evolving drug means it has a particular kind of dynamics, and that dynamics give a huge complex level of computing to compute the environment. So that is the advantage of this. So therefore, if you want to make a drug delivery system out of this dendrimer structure, what I am using, the Pamam dendrimer, people has already developed it because it has cavities inside the structure, and that cavities can be used to incorporate any small type of molecules inside that. So you can use any useful drug and take it and put it inside the pocket, and then you make a whole system. And then if you have a sensor on the top or some other means, you guide it, then it will definitely go to a particular target. And their drug release mechanism is there. You can release all those possible molecules into the system to make it functional in a particular way, very specific way. But here our system is little different because we are not talking about drug delivery system. We are talking about a drug which is itself a macro, I mean not macro in size, but in comparison to the present small molecule drugs, it is bigger in size. So it is supramolecular size. And supramolecular has the disadvantage also that the normal drug, which is actually in Armstrong size, and it can go easily bind to particular pockets of protein or DNA. Your supramolecular drug, you cannot expect that to do because it is so bigger in size that the binding interaction you expect will not happen there. So your drug will fail then. What nanobot we are talking about, eventually it should fail if the concept of the present drug activity we are considering. Because if you don't bind to a system in a biological material, then you don't expect that it will show some electronic activity or some kind of charge kind of activity so that your system will change accordingly. Because we all know that this cancer or any other kind of challenging disease which are related to either DNA or proteins are very difficult to cure because you have no access of any system which can control that. Only you have the drug design discovery system. So drug design is a kind of very, what is called, not very particular guided way. You have to develop something, you have to design something, you have to synthesize something, and then you test it. Then only if you get activity, otherwise you have to throw it away. So this kind of things is continuing for last 200 years. But now we are trying to change the thought process. We are talking about that why to bind to the system of the biomaterial, why not to control by the electromagnetic energy sending to the system so that that biological material which is very close to that particular kind of device we are sending will automatically change its conformation, what is required for the disease to be addressed. So this type of device we are talking about here, and there to generate that kind of level of energy or that kind of electromagnetic guiding force, we need a dynamic system. We cannot just put a drug delivery system there so that it can go and reside there as a standby observer. It should work there also. And they are here to survive also because it's a very hostile environment. there are so many proteins who are aggressively working into the cell, which can immediately kill the foreign substances and pick it out from the system. But you have to survive there also to make a friendship there in the environment. And accordingly, you have to understand the situation of the environment, and then you have to put your job there. So there you need some dynamic molecule, which is called molecular motors or molecular machines. So these molecular machines are very relevant these days for this kind of research, because earlier the molecule which are used to be considered as drug, even these days we are discovering continuously, are all dead molecule. Dead means they have certain conformation only. They can go cis, they can go trans, they can go S, they can go R, or certain kind of conformational rotamer changes. But it is very static. It is not dynamic. With time, it's not changing much. If you have a particular type of crystal structure, you send a drug, it will remain in that structure for long time, how long it can stay inside the system, in the biological environment, and after that it has to go out of the system. But if you have a system which is intelligent enough to just make it survive inside the system, avoiding all kind of hostile things by making changing conformation or changing electronic dynamics, then they have to be very flexible in that practice. And there molecular motors or rotors, those are very helpful, because these rotors and motors are very flexible molecule which change conformation in 360-degree way, and with time domain you cannot predict what time that rotation will come to what conformation. So they are changing dynamics, and changing dynamics eventually directly does not affect the system, but this changing dynamics eventually create certain level of frequency, resonance frequency, that can be transferred to the target system. And there you can make certain changes by using that resonance energy absorbed into the system. Because we know when molecule absorb energy, then it go to the excited state. When it release energy, it comes down to the ground state. So DNA, suppose I am trying to modify a DNA structure, which is malfunctioning. There are certain base pair not working properly. Then how come you can control them? You have to excite them with energy. So you transfer some energy from your system to that system, then it go excited state. And excited state has the ability to change their conformation. And when it release ground state, release energy and come to ground state, maybe that conformation which was actually responsible for that malfunctioning has been restored to a normal state. And that's way you can get a normal type of behavior of that DNA to restore the normal function. Otherwise, you just kill the DNA directly, like we do our present-day drug do. That they bind to a DNA and they particularly damage the DNA such a way that it does not exist anymore, and the cell die eventually. That's why we kill normal cell also with this chemotherapy drug these days.
Right.
So these are the differences.
Doctor, can you elaborate on this? When you're talking about these molecular motors, molecular machines, which are self-evolving, they are intelligent, what can it do at this point in time? And what do you think it could do in the future of, when you talk about healthcare, what else can it do for the healthcare? It will be great if you can elaborate on that.
So if I want to little bit give you the history of molecular motor and this molecular machine research, then in 1976, from that time, this has come to the scenario that this kind of molecular dynamics can be used particular purposes. And there the concept came after the great lecture by Feynman.
Richard Fineman.
In 1959. Yeah. He talked about that we can design molecules in a way that it will eventually serve your purpose of machine in nanoscale domain or this molecular scale domain. And this machine structure and the normal molecule is that you have a translational or rotational motion in the system of that kind of molecule where other molecule doesn't show it. Now, why use to do that? Because if you change the molecular structure with time, then that can produce certain kind of work or force which can be implemented in the nanoscale domain work, where you need to build something very precisely. Like I'm telling you, giving example, that this day we do nanolithography. So nanolithography, what we do, we take certain material, maybe gold, maybe platinum in liquid state or something, and then we put very thin nanoscale or microscale structure using this macro machine. But there are defects. Why there are defects? Because you cannot go into the micro level, you nano level. So definitely at the surfaces, there will be many defects which may hamper your actual conducting an experiment or getting a result or output in an accurate way. So if you have a structure which you can make a solution and then put it with a macro machine, and then it will automatically arrange itself in a way dynamically to give a structure which would be more I mean kind of defect free, and therefore your surface will be so precise to get a output accurate way that you cannot imagine. Similarly, suppose you need to make a protein sequence. So this day what we do, we have protein synthesizer. So we put some amino acid there, and then accordingly we switch on, switch off the button so that certain amino acid comes, do the reaction under this this microwave condition, and they get fused and give a chain. So in this way, you can make peptides in synthetic laboratories. But what you are doing actually, you are doing it radio frequency, because microwave is a radio frequency. You are energizing it and doing the reaction. But the problem is that you cannot control how and what condition this atomic level reaction will happen from the outside machine. So you need a inside intervention thing, which is here microwave radiation. Now you see, if I have a separate structure which is there, suppose a rotaxane molecule that already published in literature by some group, that if you have a rotaxane structure and you just put some amino acid into the solution and then you allow them to functionalize, then this rotaxane is designed in a way like DNA coding. Suppose it is coded in a way that particular that sequence amino acid will generate a particular peptide. There will be no defect. But in macro scale peptide synthesizer, you cannot, that kind of precision you cannot get. You get 60%, 70% up to that. After that, there will be certain impurities there in the system. So 100% accuracy you cannot bring by your common macro scale machine. There, your nanoscale machine that we call molecular machine can be helpful to do the job in a precise and perfect way so that you can 100% accuracy. So here also I'm talking about suppose our nanobot. Our nanobot we are implementing into cancer. So see, we already talked about DNA level interaction. So suppose we all know that the same DNA structure is just little altered in cancer cell, and that's why cell, normal cell and cancer cell are different. But you cannot identify them from the outside, but you can identify them from their behavior only. That something is rapidly proliferating, sometimes rapidly, continuously growing up. So that is cancer. But normal cell regularly cell division happen, and proliferation is very controlled. That's why it is normal. But in the cellular level, you cannot identify them because you have no tools to do that. So there you use certain marker to collect that, okay, if this is cancer cell, there should be certain marker off or on. If some on marker, then you collect them in quantity and then identify that whether the marker is actually responsible for cancer or not. If it is there, then you identify it as cancer. And certain marker you observe is off, means normal cell you get that protein, but or DNA, or cancer cell you don't get it. So these you can screen them, identifying the marker also. But you have to solve the problem, means you have to get cured. You have to give a health care. There, how to control it, how to identify a normal cell and cancer cell separately. There we cannot use our brain. There we need a system which inside the system will go and uh, collect the information and eventually give the output of their decision so that it works. So these are the things. For example, I am giving another experimental evidence for our case that we designed a maze. Okay, we designed a maze, very complex maze. From simple maze to complex maze, we have solved everything with our molecule. So there we have the microinjector. So we created one domain where there are cancer environment, one domain normal environment, and one domain is just there is no cell at all. It's a common environment, it's a normal environment. So normal cell, common environment, and cancer cell. Three domain is created, and we create the pathway. And then at a start point, if we inject that molecule in the solution and observe the emission pattern, because our molecule fortunately gives some autofluorescence from its structure. So we can easily track them under a microscope with fluorescence guidance, fluorescence guided light. There we see that it particularly traveled to the particular target, means cancer. If you see, if it's going to cancer only, not to the normal, not to the without cell environment. And also it is traveling by the path which is the shortest path. So both way you can see the amazing behavior of that small tiny nanoscale molecule, that it is deciding, it is controlling its movement, because it's a dynamic system. It has rotor on side, on the top of the molecule we have designed like that. So it can swim through the solution, but it has the liberty to go anywhere, but it is restricting itself to go not to anywhere but to particular target. So these are the things which we cannot imagine from our macro scale environmental, macro scale developmental science.
Right.
We have to go into the nano domain.
In the course of the conversation, you mentioned about Eric Drexler's book about the engines of creation. He has this concept of a molecular assembler where that's just his concept. And Ray Kurzweil thinks that maybe in the next, possibly, I don't know, couple of decades, we should be having like a molecular assembler. And once we get that, that means like we should be able to kind of 3D print out anything and everything, because we are all made out of atoms, atoms and like everything that we see, like touch, feel, the entire universe is made out of atoms. And if we are able to kind of like tinker around with that scale, I think the possibilities become so much humongous. So I'm so very excited for the future of humanity, in every direction, in healthcare. And so Dr. When you talk about these molecular motor and molecular machines, you spoke about, the use in anti-cancer drugs, antiviral nanobots, and then you're also working in the space of Alzheimer's, health space. When do you think this is going to be a reality, and when are they going to move from the lab to the market?
In case of suppose Alzheimer, if I talk a little bit, I will not go into details, but I have certain experience that I want to share with you. This Alzheimer disease happens because of the protein, this misfolding. We all know that. and it is already established by several scientists. And also several small molecule drug was discovered to test whether this can restore this protein misfolding to a normality or not. But eventually it doesn't work much in a healthy way. So we are not very much hopeful in that direction also. So people are doing different type of thinking to different type of research. There I also tried to contribute with this nanobot. So I I actually work in the two domain. In Japan, I started this research with nanobot, and then when I went to the Harvard Medical School in Mass General Hospital, I did my second postdoc there with Dr. Rudy Tenji. There I observed that if the nanobot is not there, is it possible just to send radio frequency to manipulate your misfolding of your protein? So I tested that experiment also there. So in case of nanobot, I was successfully observed that if you have this beta plaque structure, which we got from Australia, some laboratory they supplied us, uh, so that has a very complex, this scale-like thing, very tough, very rigid. So in macro open eye, you can see that so rigid it is. So even in the micro scale, micrometer scale, if you observe under microscope, then it will be so huge to observe that you cannot just confirm that what is texture, what actually the structure is. But definitely under scanning electron microscope, if you observe those structure, you will see the beautiful clustering pattern. Somebody has clustered there, like you feel that so many designed structure is so organized way this beta flake are formed. It looks very nice, but it's a dangerous killing material for human being. So we used our nanobot solution and just mixed them together to observe that is nanobot has any potential to deal with this kind of very rigid protein aggregation structure to solve. And fortunately, we observed that after 24 hours time, the same structure, what was very organized, well-crafted thing under this scanning electron microscope, get completely ruptured to pieces, and small particle in nano size has come up from the surface. So there we get a hope that yes, so we have come to a point that a system is there which lot of drug cannot do, but it using its vibrational dynamics, it can induce resonance energy to break the protein structure also. Because when a normal protein in our body is functioning, it has alpha helix in its structure mostly. Some beta sheet part are there, but mostly you will see the secondary structure, not tertiary structure. But when this protein get misfolded into a system, when it become non-functional, then all alpha helix turns into beta sheet, and it get rigidly, tightly bound like a surface, and it completely stop functioning and create poisoning inside that environment. So beta plaque is also same. The beta plaque structure derived from the Alzheimer's is the same, happens because of protein misfolding, and it is a beta sheet. So nanobot has the potential to break beta sheet structure also into pieces, and it can help. It can help to cure that kind of diseases. So from this idea, when I went to Harvard, I tried to observe that okay, already we have tested with our nanobot structure to send the resonance frequency. Now, can we test by directly sending radio frequency to the system whether it can help to break the protein structure? I started another experiment there. In there was the advantage of getting access to all kind of Alzheimer disease stuff. So immediately I joined and I get some amyloid beta protein. So amyloid beta protein is a monomeric protein. Amyloid beta protein is a monomeric protein. You can synthesize in laboratory also by artificial means. That protein, if you give particular environment, it turns into beta sheet. So what we similarly call as amyloid beta plaque. So you can create beta plaque in the laboratory test tube, and then getting that characterized under scanning time, transmission electron microscope, the structure I studied. Then I sent a radio frequency to observe what particular change we can see after sending this frequency. So you will be surprised to see. I not want to disclose in public that research idea. Observation clearly, because that is other laboratories work. So I will not go into very deep, but I can see you that I get amazed to see that at particular frequency you restored the protein structure.
Amazing work, doctor. I mean, right from your molecular motors, molecular machines to these resonance frequency technology, what are they doing is possibly, they're in the near future, they're going to be completely reimagining how we kind of do healthcare. Would you want to leave our audience behind what the future of healthcare is going to look like once these molecular machines, molecular motors, these resonance frequency technology that you're talking about takes over? How is the healthcare going to get completely upended? So maybe it would be great if you could paint a picture of what the world is going to look like in the next 10 years when we have these molecular motors, molecular machines, peering down to the nanoscale and doing some magical stuff for the healthcare.
Okay, so here I'd like to first mention that this area of research is not actually limited to me anymore, or Dr. Oniban anymore. We have already extended our collaboration, and there are great cancer biologists who has come up with to join us, like Professor Ajay Kunnamakara from IIT Guwahati in India. Dr. Snehasikta Sarnokar from CSIR ICB. He's a retired professor. And then Dr. Jimli Manna and Dr. Vain Chatterjee from IIT Kharagpur, who are doing this kind of artificial intelligence test in their devices. So definitely we are getting ahead with this designing and our concept as well as the testing. So eventually, I am very hopeful that the direction we are moving forward, it is not only limited to nanobot design and development, but it will also go beyond that, and we will be able to discover many other useful molecular motor driven functional devices which could be useful in our practical life. So there I can mention that I'm also planning to synthesize certain what is called this fluorescence dye using those molecular motors, because generally a particular molecule has a particular absorption and particular type of emission, and that particular type of emission may be in different range or single range. So particular white color or different colors it can generate, but you cannot control that molecule with time to change its fluorescence pattern according to your choice. And there your molecular motor may helpful, because you have same dye for DNA to stain, or same dye to stain your protein or ribosome or some other thing, just to changing this molecular rotors or motors conformation with time. So therefore, changing fluorescence can be developed using this kind of molecular motors in practical situation in bioimaging someday. That I'm very hopeful. Another is energy device. I have already discussed about this observation in our laboratory. So these type of advancement is definitely will help this molecular machine to go further. And then, yeah, uh, So we can continue into that direction to think about, and definitely we'll find something new,
Perfect.
exciting.
Perfect. Perfect. Doctor, really, really appreciate you taking time and being part of the podcast. I think the future looks very bright with researchers such as yourself who are looking at an extremely unique way of doing healthcare. While the world is zigging, you are zagging. So I hope that what you guys are doing when peering at the nanoscale, we discover these new novel way where we find that, okay, the healthcare can be completely upended. So more power to you and the entire team that who are working in the space. And to my
So
listeners, if you like what,
one small
yes,
thing I just want to
yes,
mention, if you
yeah,
allow me,
yeah, please, let's play.
just a healthcare thing you are mentioning. That's why I'm making this point very relevant for the discussion. So when you add this nanobot structure into the cancer cell and it affects the cancer cell, we get an surprising observation that all the DNA inside the nucleus which interact with this nanomachine get a particular shape of circular shape, and they all get self-assembled into the nucleus structure on the surface of the nucleus, and eventually it disappears by breaking up. So this is a very good observation we observed recently uh, by our student working Poroma under this Professor Punamakara. So this actually, very connecting to the healthcare with our nanobot, because now we are deeply diving into the mechanism of the cancer pathways. So yeah.
Lovely stuff. So more power to you and your team and into these new discoveries, and even the self-assembling of these atoms, these molecular structure. It's so amazing. How does it do that? It's a completely topic in itself. But really, really appreciate you taking time and being part of the podcast. To my listeners, if you like what you see in here, then please press the subscribe button. Until next time, see you guys. Bye. Thank you. Thank you, Doctor. Really appreciate it.
Thank you so much. Namaskar.